The work I'm going to present to you today is the first step of a big project which consists of building a model and numerical simulations to study vesicular release at neuronal synapses. So the first step is about asymptotic analysis of the mean first passage time of a Brownian particle to a small hole. Okay, so I will first present a short overview of synaptic transmission at chemical synapses, very short, no problem. And then I will show you the asymptotic analysis of narrow escape time. So the synapse, maybe everybody knows what it is a structure not very well known today in is the functioning that permit to transmit an electrical signal from one neuron, the presynaptic neuron, to another, the postsynaptic. So when an electrical signal arrives, an action potential in red here, it triggers the opening of the voltage-gated calcium channels, which are the blue channels on this picture. And this will trigger the entry of calcium ions within the terminal, the orange dot. And those calcium ions can go to bind to specific receptors localized on duct vesicles. The duct vesicles are the ones which are just opposed to the membrane. And if they find those duct vesicles and the specific receptors on those duct vesicles, it will trigger the release of neurotransmitter within the synaptic cleft, and then they can bind to the pink receptors, specific receptor for neurotransmitters, and the chemical cascade and everything will trigger will create an electrical signal in the postsynaptic neuron. So it's a very complex phenomenon. I'm just today interested in what's happening in the presynaptic part when calcium ions enter through the calcium channel and have to find the very small receptors located at the duct vesicle. Okay? So just a zoom on this part. So the duct vesicles are really attached to the membrane through the snare complex, which is a complex of protein. And on the snare complex, you have the receptors for the calcium. So calcium enters through the blue channels, then they diffuse, and if few calcium, like 4 to 8, find the receptors, then the synaptic vesicle will fuse with the membrane of the vesicle with the membrane, and then everything will start for the transmission. So the model here that we did is calcium ions are Brownian particles that diffuse freely in the terminal. We know that calcium ions are charged particles, but we will neglect this as the first step. And the duct vesicle is just a sphere tangent to the plane. Okay? Here you have the sphere in green and the tangent plane in blue. And the binding on the snare complex is when the Brownian particle will find the red cylinder you can find here. So this is our model of these ions finding the complex. Find the small cylinder here, which is the center of the cylinder is the center of the tangential point between the vesicle and the plane. Okay? So we are now interested in the time and in a further step of the project, the probability that an ion starting from this channel will find this small cylinder. Okay. So I will present now the asymptotic analysis we did for this narrow escape time. So the narrow escape problem we have here is the following. A Brownian particle is described by a stochastic equation. X dot equals square root of 2d w dot. D is the diffusion coefficient of the particle, and w dot is white noise. And the first time to exit domain here omega bar, which represents the domain we're interested in, through the small hole in red, the cylinder in red in this picture, is given by this. So the first time the particle finds the domain. Okay, the particle is reflected everywhere on the border of the domain, except at the red cylinder where it's absorbed. So we are interested in the mean first passage time to this cylinder, which is u of x. And we know, it's very well known, it's Dinkin, that this mean first passage time follows the solution of the mixed boundary value problem which is here d Laplacian u equal -1, d is diffusion coefficient. Du dn equals 0 is a classical reflection at the boundaries, and u equals 0 is a classical absorption at the red cylinder here. So we are going to try to find the asymptotic analysis of this time. Okay, so the first stuff we can see when we look at this domain is that it's invariant per rotation around the axis delta here, which is very easy to see. And according to the equation we have, we know that this problem is independent of theta if we consider the cylindrical coordinates around delta. So we can just study an equivalent problem in domain omega, which is a 2D domain, the projection of the domain on theta equals 0, for example. So on this domain, you see the blue is going to the blue. The red sphere is here, the red arc of circle. The small cylinder is now just segment. Okay, and the equation becomes the following equation, where you recognize here the Laplacian in cylindrical coordinates, very simply. Okay, so I'm now in a 2D domain with a 2D problem, which is equivalent to the problem we had in 3D. You notice as well that I put the diffusion coefficient on the right, and that we have reflection on the blue, black, and green boundaries, and absorption at the red segment. We are interested in the asymptotics of u when epsilon, which is the length of this segment, goes to 0. Very small, goes to 0. It's very small in front of the rest of the boundary. So the problem we have here is that we have a singularity, because when epsilon goes to 0, the point here is not regular. So to desingularize this singularity, we will have to, okay, the problem of this singularity is that it prevents us to use the classical methods, which are, for example, the green function on this domain, because we don't know the order of the green function in epsilon at the singularity. It depends on the domain, and we don't have access to this. The other method, which is very classical, is matching asymptotics. So we try to find a solution near the cusp, near the hole. We try to find a solution in the domain. We try to match, and then we can obtain something. But here, because of the geometry, it's not possible as well. So the idea is to desingularize the singularity. And we are using conformal maps. So here, because we have tangent circles, we will use the inverse map, which comes very easily when you start to think about it, because it will transform this domain into the domain tilde omega we have here, because the inverse map will transform the sphere tangent in 0 into parallel straight lines. You notice that the small hole here in red is going to a straight line here, and you know that inverse maps are putting spheres, circles into straight lines and straight line into circles. So in reality, the hole here is not a straight line, it's an arc of circle, part of a circle, but the radius of this circle is 1/2 Ra, which is here the abscissa of the hole. And if you maybe don't remember, because I didn't tell you this before, Ra is in order square root of epsilon. Okay, it's a simple computation. So this means that this at the first order we can consider that this part is straight line. Okay, the first order is straight line. So setting v of st equal u of rd, we can now consider the equation in the map domain, which is much simpler domain, because at the first order it's like rectangular domain. The equation is much more complicated because it captures the geometry of the problem in omega, but still the domain now is much easier, and we get this equation. We have the reflection dv dn again on the blue, black, and green boundaries, and the absorption on the red boundary. So to solve this equation, we will now use a scaling a scaling method. So we put zeta equal s square root of 2r epsilon, square root of tilde epsilon, okay, which means that our interest is in the region very close to the hole, okay, so very close to the red boundary. So by setting this, using the scaling, we can put big Y equals of psi t equals V of st, it's very simple. And then we can do a regular expansion of big Y in power of epsilon tilde. And injecting this regular expansion into the equation and expanding the equation now, we obtain here the asymptotic of the equation in power of epsilon. And we will now take care of the terms of much interest, leading order terms of the equation. The first one is in 1 over tilde epsilon square, then the second one is 1 over epsilon, etc., etc. So using this expansion now, we are looking, because we are looking for asymptotic analysis, we are looking of the leading order term, we will first consider the first term, which is the second derivative of y0 over t equals 0. So using this equation and the boundary condition we have on the blue and green boundaries, we can show very easily that y0 is independent of t. Okay, this is what we get from the first term. The second term, the second order term gives us this equation here, and integrating over t again, we can show that y1 is as well independent of t. It's simple computation, and using this we obtain an equation for y0 in zeta, and using the boundary condition now at the hole, which say that in zeta equal 1, the solution equals to 0, we obtain the form of the leading order term of the solution, big Y0, near the hole. Going back into our first parameters, we have that V of st take this form. Okay, so it's equals to 0 near the hole. This solution is an approximation, is not an approximation, it's the leading order term of the solution near the hole. Okay? Our problem is we have to compute A. So usually you use the rest of the parameters, but this approximation of the solution is not good far from the hole. So we cannot use the reflection, the last boundary condition we get. So to compute A, we will use the divergence theorem, which says that the integral of bar omega of Laplacian u is equal to the integral of the border, very classical equation. So this, the Laplacian u equals minus the volume of tilde omega over d just comes from the equation, d Laplacian u equal -1. And the other part, because we have reflection everywhere except at the hole, say that this integral on the border is exactly the integral of the solution at the hole. It's good because we have a solution at the hole. So we can then, using our first order term of the solution at the hole, give this equation and then find A. And we now have the first order term, the leading order term of the solution in epsilon for the whole domain. So to get tau, to get the mean first passage time, we just put the value of A in V of st and then consider when S is equal to 0, when we are far from the hole. S equals to 1 at the hole, S equals to 0 for the hole, and we get the mean first passage time for our Brownian particle to the small hole. And in the boundary layer, we also have the leading order term of the mean first passage time, and we know as well the way it behaves. Okay, so we computed the leading order term of the mean first passage time to a small ribbon located between two tangent spheres. And we could show that this mean first passage time is constant outside of the boundary layer, as we just noticed, and is well this tells us that this mean first passage time is well approximated by a Poisson process. So this is a result is already known. So it means that we can consider that the arrival of this particle to this small hole is Poissonian. And the first approximation, the law of arrival, is an exponential. This is very interesting because using this analysis in further development of the project that I don't have the time to present here, we could compute as well the probability when the particles start inside the boundary layer, because here we have the mean first passage time to go to the hole when you are far from the hole, because we said S equals to 0, so it means we are far. What's happening when you are close? The problem is still a problem. So using the same kind of analysis, what we have here, we could compute the probability to reach the cylinder before escaping the domain. Okay, it's the same kind of computation. And using this, we could build a model of the active zone, which is the place where vesicles are located and the calcium channels are located as well, to investigate the influence of the position of the channels on the crowding of vesicle or not crowding of vesicle, etc., on the release probability, which is the probability to have the fusion. So the probability to have 4 ions that are coming to this vesicle or not. And using this, we could build a model of the presynaptic terminal, much bigger, with the whole stuff we have over there. And the fact that this mean first passage time is Poissonian is really what is important here in our study, because if you want to model the presynaptic terminal, you have a Brownian particle. You can do Brownian simulations if you want. It's very simple. Not that simple because the domain is not that fun, but okay, you can do it. But you will wait for hours because of the very small hole you have here, and because of the very long time you have to find this small hole. The fact that it's a Poisson process allows you to use simply Gillespie algorithm to say, okay, it's Poissonian. I can at least use Markov chain for what's happening because it's constant. It doesn't depend on the position, so it doesn't depend on the time. And it's what we did in the following of this project. And I wanted to show you this because it's the very first step, but everything is going after that, because we could show that the mean first pass time is independent of the position and that this time is Poissonian time. So this work was published in SciAm Multiscale Modeling and Simulations. So I want to thank just my PhD supervisor, David Altman, and my lab mates, and the organizer of this conference for giving me the opportunity to present my work today. Thank you.
Is there any questions?
I was just wondering, what do you mean by it's well approximated by a Poisson process? I mean, the first passage time is approximately exponentially distributed?
Yeah, exactly.
Because of this metastability?
Because it doesn't depend on the position, in fact. So it doesn't depend when you start. So it's, yeah. You have the mean, the variance is the same, and it's well approximated there.
Any other questions? Well, if not, let's thank the speaker again.